Soft drinks are a billion-dollar blend of chemistry, flavor, and fizz that captivate the world. From Pepsi's bold cola formula to Fanta's fruity burst and Dr. Pepper's mysterious 23 flavor mix, each soda is a masterpiece of carbonation and taste engineering. Today, we dive inside their bottling plants to see how these legendary drinks are brewed, blended, and bottled for that unmistakable pop. Pepsi begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5:1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens, and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collator arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces, syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drink's base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottleneck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coded, checked, and shrink-wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coding, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. The core of Coca-Cola's production begins at the local bottling facility. These factories are strategically located around the world to minimize transportation time and maximize freshness. While the Coca-Cola Company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and checkweighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into six-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remains simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, from syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. To begin understanding how Dr. Pepper is made, we have to step inside one of the massive regional bottling facilities operated by licensed partners. These plants are the heartbeat of the Dr. Pepper supply chain. They don't just bottle soda, they engineer precision, maintain sterility, and manage staggering volumes of ingredients with scientific exactness. Everything begins with water. Although soda is often celebrated for its flavor, more than 85% of the final product is purified water. And not just any water, ultra-clean, neutral, flavorless water that forms the foundation of every bottle. This means municipal or groundwater entering the plant must undergo intensive treatment. The first stage of this treatment process uses coarse filtration to remove large particles and suspended solids. Then, the water is passed through activated carbon beds to eliminate chlorine, chloramines, and any volatile organic compounds that could distort the flavor. From there, the process shifts to more advanced techniques. Reverse osmosis membranes, or ultrafiltration units, strip the water of minerals, microbes, and trace contaminants. Ultraviolet light, or ozonation, finishes the process, sterilizing the water and rendering it free of any taste or odor. The water is now ready, perfectly clean, chemically stable, and ready to receive the flavors that define Dr. Pepper. Parallel to this, syrup preparation takes place in a separate, sanitized mixing room. The base flavoring for Dr. Pepper arrives at the plant in concentrated form, pre-blended by the brand's flavor division under tight secrecy. These concentrates are stored in stainless steel containers and handled with care, with operators measuring and metering the required amounts into large batching tanks. In these tanks, often fitted with high shear mixers, agitation paddles, and precision load cells, the base concentrate is combined with purified water, sweeteners, and acids. Depending on the region, the sweetener may be high fructose corn syrup or cane sugar. The acid, usually phosphoric or citric, helps balance the syrup's pH and sharpness. The mixture is stirred and recirculated until it becomes a uniform, homogeneous syrup with exact Brix values, the measure of dissolved solids in a liquid, often used to calibrate sweetness levels. Before it moves forward, the syrup batch undergoes quality assurance checks. Technicians take samples and run tests in on-site labs, analyzing Brix, pH, color, and aroma. Only after it passes these strict controls is the syrup cleared for the next phase, beverage blending. In a process called proportioning, the syrup is metered and blended with purified water in exact ratios, typically around 1 part syrup to 5 parts water. This mixture becomes the flat, uncarbonated Dr. Pepper base. The proportioning system is controlled by flow meters and programmable logic controllers, ensuring that the mix is stable within a tight tolerance band. Every shift, every batch, whether it's in Texas, Ontario, or the Philippines, must deliver the same flavor profile. With the beverage mixed, it's time to add the fizz. Carbonation is one of the most technically critical steps in soda production. The pre-mixed Dr. Pepper is chilled to just above freezing, typically around 35 degrees, to increase its ability to absorb carbon dioxide. CO2 is stored in large tanks on site and is food grade, filtered, and monitored for purity. The cold liquid is forced through a carbonator where fine CO2 bubbles are injected under high pressure through porous diffusers or sintered steel plates. Proper carbonation is both science and art. If done poorly, the soda may foam excessively during bottling or taste flat when opened. The target for Dr. Pepper is usually around 2.5 to 3.0 volumes of CO2, enough to give it its characteristic zing without overwhelming the complexity of its 23 flavor blend. The carbonated product is now pressurized and ready for immediate bottling to prevent CO2 loss. The bottling line is where everything shifts into high speed. Depending on the plant, the line can handle glass bottles, aluminum cans, or PET plastic bottles. Most modern facilities use stretch blow molding machines to convert PET preforms into full-sized bottles on site. This reduces shipping costs and allows for rapid size changes depending on demand. Each bottle or can first passes through a rinsing or sterilizing system. Bottles may be inverted and blasted with ionized air or washed with ozonated water. Cans are typically rinsed with sterilized water before entering the filler. Now, the carbonated Dr. Pepper is dispensed into containers using a rotary filling machine. This machine features multiple filling heads rotating on a carousel, with each head delivering the precise amount of liquid into each container. The filler operates under pressure to prevent foam and retain carbonation. As soon as the beverage is deposited, the bottle or can is sealed. PET bottles are capped using torque-controlled screw heads, while cans receive crimped-on aluminum lids in a high-speed seamer. Immediately after sealing, the containers pass under printers that apply batch codes, production dates, and expiration information. This coding is essential for traceability. If there's ever a recall or quality issue, the plant can trace every bottle back to the exact minute it was produced, the syrup batch used, and the operator on duty. Then comes packaging. Filled bottles are grouped into packs using shrink film, cardboard sleeves, or trays, depending on the final retail format. These packs are stacked by robotic arms onto pallets in precise configurations optimized for transport. The finished pallets are stretch-wrapped, labeled with shipment data, and moved to the distribution warehouse. But before any pallet is cleared for shipment, the line's quality control team pulls samples from each production run. These are subjected to rigorous testing in the plant's on-site laboratory. Pressure tests confirm carbonation levels. Spectrophotometers check color uniformity. Sensory experts conduct taste evaluations to verify the blend is balanced. Microbial samples are incubated to ensure the product is sterile and safe. Meanwhile, automation software monitors the entire plant. From SCADA systems that track syrup bricks and carbonation pressures to IoT-enabled sensors that measure temperature drift in holding tanks, the entire operation is visible in real time to engineers and technicians. If a motor starts to overheat or a fill level goes out of spec, alerts are triggered immediately. Once quality is assured, the finished product is ready for shipping. Climate-controlled logistics routes transport Dr. Pepper to warehouses, distributors, and retail outlets. Some trucks are refrigerated, especially in hotter regions, to protect the product during transit. Whether it's a vending machine in a high school, a 12-pack in a grocery store, or a fountain soda in a fast food chain, each container of Dr. Pepper must taste exactly the same. And that's only possible because every variable was controlled from start to finish. Beyond the factory, the Dr. Pepper production network also includes specialty manufacturing for fountain syrups, bag-in-box formats for restaurants, and concentrate shipments for international bottlers. These formats go through similar blending, filtration, and quality assurance processes, but are tailored for bulk use with different bricks and carbonation considerations. Every day, this system repeats across dozens of plants, with millions of cans and bottles produced and shipped with extraordinary consistency. Despite being made at different locations by different teams, every unit of Dr. Pepper shares the same flavor fingerprint: sweet, spicy, slightly fruity, with a creamy undertone and a signature bite. It's a beverage born in the 1880s, but produced today using some of the most advanced technologies in food manufacturing. From its mysterious blend of flavors to its perfectly balanced carbonation, Dr. Pepper represents a legacy of innovation, precision, and a dedication to quality that extends from syrup tank to store shelf. Sprite's story begins with water. While most people focus on Sprite's citrus flavor, the truth is that over 85% of what you're drinking is water. But not just any water. For Sprite to taste exactly the same in Singapore as it does in San Diego, bottling plants must purify their local water supply to a consistently neutral baseline, free from taste, color, odor, and minerals. The incoming municipal or well water is first screened through mechanical filters to remove suspended solids. It then moves through activated carbon filters that strip out chlorine, chloramines, and any volatile organic compounds. This ensures that the water has no off-putting flavors. Then it passes through either reverse osmosis membranes or demineralization columns, which remove dissolved salts and ions. Finally, a UV treatment or ozone injection kills any microorganisms. This ultra-purified water is held in stainless steel tanks, where it is monitored in real time for pH, conductivity, turbidity, and microbial counts. It must meet the exact specifications set by the Coca-Cola company before being allowed into any part of Sprite production. Only once it's passed all quality checkpoints can it be used to create the base for one of the world's most recognizable sodas. Parallel to the water treatment is the preparation of Sprite's proprietary flavor syrup. This part of the process is handled in a syrup blending room, often kept under positive air pressure and high sanitation standards to prevent contamination. The base concentrate used for Sprite, supplied by the Coca-Cola company, is delivered to the plant in sealed, food-safe drums or totes. This concentrate contains the citrus flavoring system, acidulants, and trace aromatic compounds that define Sprite's lemon-lime taste. Inside the blending tanks, equipped with high-torque agitators and recirculation loops, the concentrate is mixed with water and sweeteners to form the final syrup. The sweetener is usually high fructose corn syrup in the United States, though in some countries, cane sugar is used instead. Citric acid and natural flavors help create that sharp, clean taste. The syrup is blended at specific Brix levels, a measure of sugar concentration, and is analyzed for consistency in labs adjacent to the blending floor. Once the Sprite syrup is blended and passes quality checks for color, taste, pH, and sugar content, it is sent to the proportioning system. This is where the final product begins to take shape. Inside stainless steel pipelines, the syrup is carefully metered and mixed with the purified water in precise ratios, generally around 1 part syrup to 5 parts water. This mixture is now the uncarbonated version of Sprite, flat, sweet, and citrusy, but still missing that all-important sparkle. Carbonation is added in the next step. The flat beverage mixture is chilled to near freezing, typically 33 to 36 degrees F, inside jacketed holding tanks. This is essential because cold water absorbs carbon dioxide much more effectively. A carbonator, one of the most critical pieces of equipment in the line, injects high-purity, food-grade CO2 into the chilled mix. The carbonation process is highly controlled. Bubble size, saturation level, and gas purity are all continuously monitored. Sprite generally carries between 2.7 to 3.0 volumes of CO2, giving it that signature effervescence and a sharp bite that enhances the citrus flavor. Once carbonated, the finished Sprite beverage is held under pressure in chilled, oxygen-free holding tanks. It is now ready for bottling, and this is where the production line hits its highest speed. The bottling line is a marvel of automation, capable of processing over 1,000 bottles or cans per minute, all synchronized to fill, cap, label, and inspect each unit with zero tolerance for error. First, the containers must be prepared. If PET bottles are used, they arrive as pre-forms, small, test tube-shaped blanks. These pre-forms are heated and stretch-blown into full-size bottles using high-pressure air inside precision molds. This process allows plants to manufacture bottles on-site, reducing shipping costs and allowing for quick changes in size or shape depending on market needs. The newly formed or delivered containers are then sent through a rinsing or sterilizing station. Bottles may be sprayed with ionized air, steam, or ozonated water to remove dust and kill microbes. Cans are similarly rinsed and then inverted before filling. The carbonated Sprite is then filled into each container using a rotary filling machine. The beverage must be filled under counter pressure to preserve carbonation and prevent foaming. Each filling nozzle is calibrated to deliver an exact volume, down to fractions of a milliliter. As soon as a bottle is filled, it immediately passes to the capping station. Caps and lids are fed in from hoppers and applied with high-speed capping heads that torque each PET bottle to specification. Aluminum cans are sealed with a crimping mechanism called a seamer, which attaches the lid using multiple rollers in rapid succession. The entire filling and capping sequence is enclosed within a clean, sterile zone to prevent contamination. With the product sealed, it's time for coding and inspection. Each unit is printed with a production code, batch number, and best before date using a high-speed inkjet or laser printer. Advanced camera systems immediately scan the bottles or cans for fill level, cap alignment, label position, and structural defects. Anything that doesn't meet specs is ejected from the line automatically. Now the finished bottles or cans are routed to the packaging area. Depending on the destination, they may be shrink-wrapped in multi-packs, inserted into cardboard carriers, or loaded into trays for larger retail formats. Robotic palletizers pick up these packs and stack them in precise layers, forming stable shipping units. Each pallet is stretch-wrapped, labeled with destination and production information, and scanned into the warehouse inventory system. Before these pallets leave the facility, the Sprite they contain has already been sampled for in-depth quality checks. Laboratory technicians pull random samples throughout each production run and test for bricks, pH, CO2 volumes, and sensory characteristics such as aroma, clarity, and taste consistency. These tests are performed hourly, sometimes more frequently, using calibrated instruments and trained panels. Additional microbiological testing ensures the beverage is free of spoilage organisms. Each batch must pass these hurdles before it is released for distribution. Some plants hold back every 10th or 20th pallet for additional hold and release protocols, where the beverage is stored under controlled conditions and monitored for early spoilage signs before shipment. From here, Sprite enters the logistics phase. Temperature-sensitive loading docks ensure that the product stays cool, especially in hot climates where carbonated beverages can suffer from premature expansion or loss of pressure. Climate-controlled trucks or standard dry vans, depending on the geography, transport the soda to distribution centers, retail warehouses, and vending machine operators. Behind the scenes, the entire operation is driven by powerful software. SCADA systems, programmable logic controllers, and cloud-connected ERP platforms. These monitor tank levels, syrup usage, CO2 flow rates, batch records, and even maintenance needs. Some lines are equipped with predictive analytics, using data to forecast failures before they occur, reducing downtime and ensuring maximum uptime. Every bottle and can of Sprite must conform to the same flavor fingerprint: balanced sweetness, bright citrus notes, clean finish, and a bracing level of fizz. Even with local water, different sweeteners, and various bottling partners worldwide, Coca-Cola's stringent standardization process ensures that no matter where you are, every Sprite you open tastes like it came from the same source. And yet, as science-driven as it is, the drink remains simple in experience. No caffeine, no color, just a bold, clear, citrus-flavored soda that delivers a refreshing hit with every gulp. A product of incredible precision, born in stainless steel tanks, shaped by sensors, robotics, and human craftsmanship, and enjoyed, often without a second thought, by millions. In the end, Sprite may be light and fizzy, but its production is anything but. It's the result of decades of process optimization, global logistics, sensory chemistry, and industrial control. And behind that cool green label lies one of the most tightly controlled and fascinating beverage production systems in the world. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water, and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B-group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically one out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. In the high-output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle, inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, can production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counter-pressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for brix levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning-in-place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine. Syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins, not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup to water ratio down to tenths of a percent so that every litre leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins, not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second. ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. It all begins long before a Dunkin Donut ever meets a customer's lips. The journey of a factory-made Dunkin Donut starts in massive industrial facilities engineered specifically for high-throughput baking and frying. Unlike the fresh, hand-prepared donuts in local bakeries, the factory-produced donuts that supply regional distribution centers or large retail outlets are the result of a tightly choreographed sequence of automated, mechanized operations, each designed to maximize consistency, food safety, and output volume. The core ingredients of a Dunkin Donut seem simple: wheat flour, sugar, yeast or chemical leavening agents, eggs or egg solids, milk derivatives, oil, and water. But each of these components must meet stringent specifications. The wheat flour is typically sourced from large milling operations and arrives at the factory in bulk pneumatic tankers. Once offloaded into giant silos, it's carefully monitored for protein content, moisture, and particle size. These parameters are crucial as they directly affect gluten development, dough elasticity, and fry stability. The sugar, often in fine granulated form, is similarly delivered in bulk and stored in temperature-controlled hoppers to prevent clumping. The yeast, which may be active dry or instant, is carefully handled to maintain viability. For cake-style donuts, chemical leaveners such as sodium acid pyrophosphate and baking soda replace yeast, requiring exact dosages to control rise, texture, and batter pH. Liquid ingredients like water and milk concentrates are pumped from stainless steel reservoirs through filtered lines. Egg solids, whether powdered or liquid, are introduced via sealed containers to reduce contamination risk. At the heart of the process is the dough preparation system. In a typical yeast-raised donut line, a computerized batching system automatically dispenses pre-weighed quantities of dry and wet ingredients into a horizontal spiral mixer, usually a high-capacity unit capable of mixing several hundred pounds per batch. This mixer blends the ingredients through a timed, multi-speed cycle. A slow initial mix to hydrate the flour, followed by a high-speed kneading phase to develop the dough's structure. Temperature probes ensure the dough reaches the optimal final mix temperature, often around 78 to 82 degrees. Any deviation can alter fermentation speed and finished product quality. Once mixed, the dough is transferred, either manually in smaller setups or via automated dough elevators in large-scale operations, to intermediate proofing cabinets. These are large chambers that maintain a warm, humid environment, typically around 90 degrees Celsius, with 85% humidity. The dough rests here for 30 to 45 minutes, allowing initial yeast fermentation to begin. This resting period improves extensibility and relaxes the dough for sheeting. From the proofing cabinet, the dough moves to the sheeting line. Here, massive rollers flatten the dough to a precise thickness, often controlled by laser-guided sensors. A conveyor belt feeds the dough through a series of increasingly fine rollers, each pressing it thinner until it reaches the exact gauge required for donut formation. Dusting flour is automatically sprinkled to prevent sticking, and scrap management systems collect unused dough trimmings to be reprocessed in future batches. Next, the formed dough sheet moves to the rotary cutter station. This is where the signature donut shapes come to life. Custom-designed rotary dies stamp out rings, holes, or specialty shapes like filled bars or seasonal themes. Each cutter is precision machined to minimize dough stress, ensuring even fry results. A vacuum system gently lifts and removes cut donuts from the scrap dough matrix, depositing them onto another conveyor in perfect alignment. These unbaked, shaped donuts are then transferred to the final proofer, a massive multi-tiered system that can resemble a vertical carousel. Moving slowly through this enclosed environment, the donuts are proofed for anywhere from 35 to 60 minutes, depending on product type and yeast activity. This is a critical phase. The dough expands, air cells develop, and the signature light texture of a yeast donut forms. Relative humidity and temperature are tightly regulated to promote even rising. Once proofed, the donuts enter the fryer. This is one of the most visually captivating moments in the factory. Rows upon rows of pale, risen dough transforming into golden brown perfection. Industrial donut fryers are long, shallow troughs filled with high-stability frying oil, typically a blend of soybean or palm oil designed to withstand high temperatures without breaking down. The donuts enter via an automated conveyor that gently lowers them onto the surface of the hot oil, held between 350 to 375 degrees. Floating racks or submerged mesh baskets keep the donuts evenly spaced and ensure uniform frying on both sides. The donuts are flipped halfway through using automated paddles or turning bars, so each side receives equal exposure. Fry time is typically 90 to 120 seconds per side for yeast-raised varieties. Throughout the fryer, oil filtration and replenishment systems remove debris and maintain oil quality, critical for flavor, texture, and food safety. After frying, the donuts move onto a draining belt where excess oil is wicked away using absorbent conveyor surfaces or air knives. From there, they transfer directly to a cooling tunnel, an enclosed, climate-controlled conveyor that gently brings the donuts down to ambient temperature. This cooling phase, usually lasting 8 to 12 minutes, stabilizes the structure and prevents condensation before glazing or filling. Now comes one of the most iconic steps: glazing. The donuts pass beneath a cascading curtain of warm glaze, typically made of powdered sugar, water, and stabilizers like corn syrup or mono and diglycerides to ensure sheen and viscosity. The glaze is held at precise temperatures, around 105-115 degrees Fahrenheit, to allow smooth coating without excessive dripping. Any glaze runoff is collected, filtered, and reused within quality limits. For filled donuts, a separate line handles injection. This is a precise, high-speed process where each donut is clamped and filled through nozzles that inject jelly, cream, custard, or other fillings. Volumetric pumps control exact fill amounts, typically between 15 to 25 grams per donut, to ensure uniformity. The timing of this step depends on whether the donut is glazed before or after filling, a decision made based on the type of coating or desired product appearance. Topped donuts, such as Boston cream or chocolate frosted, pass through enrobing units or individual depositor stations. These machines spread or pipe icing onto the surface, using rotating drums or mechanical arms to achieve even distribution. Sprinkles, nuts, or other toppings may be applied via shaker systems or robotic garnishing heads, with vacuum sensors ensuring no foreign objects are introduced. Once coated, the donuts continue on conveyors to the packaging area. Here, an optical vision system inspects each unit for shape, color, topping placement, and fill integrity. Defective products are automatically rejected and diverted for analysis or disposal. The acceptable donuts proceed into robotic tray loaders or auto packing machines. For bulk shipments, donuts may be arranged in plastic trays stacked into crates. For retail packs, form-fill seal systems wrap donuts in individual or multi-unit blister packs using heat-sealed film. Each packaged unit receives a date code and product identifier via inkjet printer or laser etching. Metal detectors and X-ray scanners stand guard just before final packaging to catch any foreign materials, from metal fragments to hard plastics. At this point, the product has passed through over a dozen safety checks, far more rigorous than what a local bakery could feasibly achieve. Before leaving the factory, pallets of donuts are weighed, logged, and tagged with RFID labels for inventory tracking. They're stored in temperature-controlled staging areas until trucks arrive. Distribution fleets, often operated by third-party logistics firms, are designed to transport the donuts quickly to regional warehouses or direct-to-store delivery networks. Because many factory-made donuts are frozen for extended shelf life, refrigerated trucks or freezer compartments maintain ideal storage conditions throughout transit. Once at a distribution center or store, the donuts are thawed if necessary and either resold in packaged form or used to stock fresh counters in Dunkin outlets. Some outlets may perform final finishing touches, like adding fresh glaze, sugar dusting, or customized toppings. But the bulk of the preparation has already occurred at the factory, where industrial consistency reigns supreme. Before a Subway sandwich ever reaches the customer's hands, its journey begins far from the store counter, in sprawling, high-efficiency food manufacturing plants that are responsible for producing the standardized components that make up the brand's globally recognized product. While each Subway location assembles its sandwiches fresh to order, the bulk of the ingredients, the breads, meats, cheeses, sauces, and even vegetables, are processed, prepared, and packaged in industrial facilities built for consistency, volume, and food safety. These components are the result of complex, multi-step production lines designed to meet Subway's stringent specifications across every country they operate in. The foundation of any Subway sandwich is the bread. While baked in store for aroma and freshness, the bread dough itself is manufactured at specialized commercial baking facilities. These plants begin by sourcing massive quantities of high-gluten wheat flour, usually delivered in pneumatic tankers and stored in tall, stainless steel silos. The flour is tested for protein content, ash level, and moisture to ensure it falls within tight tolerances required for consistent dough performance and volume expansion. Once quality is confirmed, the flour moves via auger or vacuum transfer to automated mixing systems. Each variety of bread, Italian, honey oat, hearty multigrain, and so on, has its own formula, managed by a PLC-controlled batching system. Water, sugar, salt, yeast, dough conditioners, and enrichments like wheat germ or oats are dispensed in precise quantities and sent into high-capacity spiral mixers. These mixers, with capacities reaching up to 1,000 pounds per batch, perform a sequence of low-speed and high-speed kneading to develop the gluten network necessary for Subway's springy, chewy bread texture. Temperature-controlled water and chilled mixing bowls help maintain the dough temperature, typically around 78 degrees Celsius, essential for proper fermentation. After mixing, the dough is unloaded onto transfer belts and sent into a first-stage resting tunnel or intermediate proofer. Here, the dough rests in a humid, warm environment to allow the yeast to activate and create carbon dioxide, giving the dough extensibility before shaping. Next, the dough is portioned using volumetric dividers that slice the mass into uniform weights. These pieces then pass through rounding and molding machines that elongate them into the familiar Subway sandwich roll shape. Automated flour dusters and non-stick belts ensure smooth passage through the shaping process. For breads with toppings like oats or cheese, the dough passes under a rolling applicator or static sprinkler before entering the next proofing stage. The proofing phase is critical. Dough pieces are placed onto pans and loaded into an industrial proofer, a large, climate-controlled chamber with tiered racks or chain-driven carriers. Inside, the bread rises for 45 to 60 minutes at around 90 degrees Celsius with high humidity. Dough height, elasticity, and fermentation rate are monitored using sensors or inline imaging to guarantee uniform rise. Once proofed, the dough pans move into the par baking ovens. These are tunnel or rack ovens heated to approximately 420 degrees. The bread bakes for about 8 to 10 minutes, enough to set the structure and crust, while preserving enough internal moisture so it can be finished baking in store. After baking, the loaves are cooled in ambient air tunnels before being packaged. Packaging is a delicate process. The cooled loaves are inserted into specially ventilated film or bulk freezer trays. Modified atmosphere packaging may be used to extend shelf life and prevent freezer burn. All packaging is date-coded, labeled with batch tracking, and sent through metal detectors or X-ray systems. Then the bread is quickly frozen in blast freezers that bring core temperatures below zero in under 90 minutes, preserving quality for shipment. While the bread is handled this way, meat and poultry ingredients follow a parallel but very different industrial route. Subway's deli-style meats, turkey breast, ham, roast beef, and chicken strips are cooked, sliced, or formed in specialized meat processing plants. These facilities receive USDA-inspected raw proteins that are boned, trimmed, and cleaned under strict sanitary guidelines. The raw meats are portioned, tumbled, and marinated with Subway's proprietary brine formulas, which often include salt, phosphates, sugar, and flavorings. In the case of chicken strips or patties, the meat may be fully cooked in steam ovens or grill presses, then flash frozen to lock in moisture. Roast beef and turkey, on the other hand, are typically cooked in steam ovens or combi ovens that simulate traditional roasting while maintaining high throughput. Once cooked, the meats are cooled using spiral chillers or glycol plate systems, then sliced on high-speed rotary slicers for uniform thickness. These slices are stacked and portioned by weight using automated weighing machines, then sealed in vacuum pouches or controlled atmosphere trays. Each portion is sealed with batch coating and passed through inspection systems before being packed into cartons and frozen for distribution. Cheese slices, Swiss, American, provolone, and pepper jack are produced using high-speed forming and slicing systems. Cheese blocks are first melted down, then reformed into large sheets which pass through slicing blades and portion conveyors. Anti-stick sheets are often placed between slices, and stackers organize the cheese into count-specific bundles. each packaged under vacuum or gas-flushed atmospheres to preserve shelf life and prevent molding. Vegetables such as lettuce, tomatoes, cucumbers, onions, and green peppers are not grown in factories, but they do undergo industrial preparation before arriving at each store. Lettuce, for example, is harvested, washed with chlorinated or ozonated water, and shredded in high-speed slices. Tomatoes are cleaned, visually inspected, and machine sliced before being layered between food-safe pads that prevent bruising during shipping. Onions are peeled, sliced, and packaged in gas-flushed bags to reduce spoilage and preserve freshness. All vegetables are packed in refrigerated, ready-to-use formats and delivered through cold chain logistics to ensure they remain crisp and safe for consumption. Subway's specifications for produce are among the most rigorous in the QSR industry, often requiring vendors to perform multiple microbial tests before product release. Sauces, ranch, Chipotle Southwest, mayonnaise, mustard, sweet onion, and many others are made in liquid processing plants that function much like beverage or dairy factories. These facilities handle emulsion preparation in large mixing tanks fitted with high shear homogenizers. Ingredients like oils, water, spices, thickeners, and preservatives are blended under vacuum to ensure air-free, stable emulsions. The sauces are then pumped into sterile filling machines that dispense measured volumes into squeeze bottles, bulk pouches, or portion cups. Heat sealing, tamper-evident caps, and nitrogen flushing preserve shelf life. Every component, from bread to sauce, is designed with logistics and final assembly in mind. Once all the parts are complete, they're loaded onto pallets, sorted into refrigerated and frozen shipments, and transported to Subway's distribution centers. From there, truck routes are carefully scheduled to ensure timely delivery to thousands of store locations. All products are scanned, tracked, and recorded during shipment, ensuring cold chain integrity and traceability from plant to sandwich counter. Inside the store, the staff becomes the final assembly line. Each morning, the frozen bread dough is thawed and given a second proof before finishing its bake in the store's convection ovens. Meats are defrosted and held in refrigerated bins, vegetables are placed into prep trays, and sauces are opened and loaded into squeeze bottles. Sandwich artists follow precise build sheets and portioning guides to ensure a consistent experience for the customer. Even at the store level, there are echoes of the factory's precision. How many ounces of lettuce per 6-inch sandwich? How many slices of meat? What angle to cut the bread? It all comes back to what was engineered upstream. Without the highly standardized processes in the manufacturing plants, the in-store experience wouldn't feel as predictable and familiar across the world. The industrial journey of a Chipotle meal begins with ingredient sourcing. Chipotle is known for its emphasis on food with integrity, which means that much of the upstream processing is tightly controlled, even before the factories get involved. The chain sources meats that are often antibiotic-free, pasture-raised, or sustainably farmed. These meats arrive at centralized processing plants, some Chipotle-operated, others contracted to third-party co-packers, with exacting specifications. Take chicken, for instance, one of Chipotle's most popular proteins. Whole chicken breasts and thighs are delivered from certified suppliers in refrigerated transport and immediately placed into cold storage bays at the processing facility. These facilities are equipped with advanced sanitation systems, including antimicrobial entry zones and HEPA-filtered air circulation to maintain a sterile environment. The chicken is deboned, trimmed of excess fat, and portioned into standardized sizes using automated cutters. Optical sorters with high-speed cameras and laser detection systems inspect each piece for defects, bone fragments, or inconsistencies. After cutting, the chicken moves into industrial tumblers or vacuum mixers where it is marinated. The marinade consists of oil, spices, garlic, citrus juices, and chipotle pepper, all pre-mixed in large blending tanks. These tumblers are designed to evenly coat the chicken while tenderizing it, using a slow rotational motion that lasts anywhere from 20 minutes to several hours, depending on the specific formulation. The chicken is then sealed into vacuum-packed pouches or bulk containers and flash chilled. In many cases, the chicken is shipped raw to Chipotle locations, where it is grilled fresh daily. However, in higher volume markets or during peak operational periods, some portions may be pre-cooked using commercial-grade combi ovens or grill presses inside regional commissaries. These ovens are steam-injected and heat-distributed, ensuring that the chicken reaches internal temperatures of 165 degrees without losing moisture. After cooking, the chicken is cooled through rapid chill spiral systems that reduce the temperature below 40 degrees in less than 90 minutes, in compliance with USDA food safety standards. Now let's move to beef, specifically the barbacoa and steak options. These are handled in meat facilities equipped to manage tougher cuts like shoulder clod or round for barbacoa, and sirloin or top butt for steak. The barbacoa beef is typically seasoned, seared, and slow cooked in massive steam kettles or pressurized braising tanks. These tanks operate on programmable logic controllers that maintain precise temperatures and cook times, allowing the meat to tenderize while absorbing the bold, chipotle, and cumin flavors characteristic of the dish. Once fully cooked and shredded by automated paddles, the barbacoa is portioned into pouches and vacuum sealed. It's then rapidly frozen using cryogenic tunnel freezers, often with liquid nitrogen or CO2, to preserve texture and moisture content. Steak, on the other hand, may be seared and sous vided, then chilled and packaged for final grilling in store, allowing for that signature charred flavor upon finishing. Beans, both black and pinto, are another central component of Chipotle's offerings, and their factory preparation is highly systematic. Dry beans are received in bulk sacks and stored in silo bins, where they undergo cleaning, sorting, and rinsing. Industrial bean cookers, large rotating steam kettles or pressure vessels, hydrate and cook the beans using temperature and pressure sensors to ensure that every batch hits the ideal softness and moisture level. Chipotle's beans are often seasoned with bay leaf, garlic, cumin, and salt, and held in stainless steel jacketed tanks for blending. After cooking, beans are cooled, portioned into food-safe containers or sealed bags, and transported under refrigeration to stores, where they are reheated and seasoned further before serving. Some regional commissaries may do the final seasoning step in-house, using proprietary spice blends and steam kettles to reduce in-store labor. Next up is the rice, a deceptive salsas like the mild tomato salsa, corn salsa, and spicy red chili version are produced in facilities that combine both fresh vegetable processing and sauce manufacturing capabilities. Roma tomatoes, tomatillos, onions, and jalapenos are washed, diced, and de-seeded by high-speed dicers equipped with antimicrobial wash cycles. The chopped ingredients are portioned into blending tanks, where citrus juice, cilantro, salt, and spices are added. These tanks are chilled to preserve freshness during mixing. The salsas are filled into containers using multi-head fillers, which ensure precise weight and avoid overfilling. Each container is lidded, labeled, coded, and passed through X-ray or metal detection systems before being boxed and shipped under refrigeration. Because Chipotle prides itself on using fresh, preservative-free salsas, the cold chain must be rigorously maintained, and shelf life is generally short, often under 7 days. Guacamole is arguably one of Chipotle's most iconic items, and it, too, is partially factory-produced to reduce in-store prep time. Avocados are shipped to processing plants where they are ripened in ethylene-controlled ripening rooms. Once they reach optimal softness, they are halved, pitted, and scooped using semi-automated systems. Some facilities still rely on manual scooping to preserve texture and quality. The avocado pulp is then mixed with red onions, cilantro, lime juice, salt, and jalapenos in large mixing vessels outfitted with slow-speed paddle blades to avoid over-pureeing. The finished guacamole is portioned into food service containers and sealed under nitrogen-rich modified atmosphere packaging to prevent oxidation. These are chilled and shipped directly to stores, where they are used within a few days. Even toppings like shredded cheese and lettuce are processed off-site. Cheese blocks, such as Monterey Jack and white cheddar, are shredded using rotary shredders that minimize clumping and deliver consistent length and thickness. The shreds are dusted lightly with starch or cellulose to prevent sticking, and then packaged in gas-flushed bags. Lettuce, typically romaine, is shredded, washed, triple rinsed, and run through centrifugal dryers before being packed in bulk bags with breathable liners. All of these components, once prepared, are transported through a tightly managed distribution network. Refrigerated trucks, monitored with GPS and temperature sensors, deliver ingredients to regional distribution centers or directly to restaurants. There, store teams receive shipments, log temperature compliance, and rotate stock to maintain freshness. From an industrial standpoint, the brilliance of Chipotle's system lies in its hybrid model. It doesn't fully outsource prep, nor does it rely completely on in-store scratch cooking. Instead, it shifts labor-intensive, food safety-sensitive processes like meat marination, slow cooking, salsa preparation, and bean cooking to industrial plants, while retaining finishing touches like grilling, assembling, and seasoning at the store level. This allows the brand to maintain the perception and flavor of real food without the variability or inefficiency of completely decentralized preparation. Behind the scenes, teams of food scientists, process engineers, and quality assurance technicians work constantly to refine this supply chain. They use high-resolution cameras, digital sensors, and real-time tracking to ensure consistency from one end to the other. Batch codes, microbial testing, and predictive analytics help catch problems early. Whether it's an out-of-spec chicken marinade or a salsa with an inconsistent heat profile,